So, as promised in section 5.1, cs407 is proud to present the Romberg algorithm for numerical integration for your enjoyment and pleasure. So, the Romberg algorithm produces a triangular array of numbers, all of which are numerical estimates of the definite integral from a to b of f of x dx. And in particular, it produces a table beginning with r00 in the first row and first column, all the way down to rnn. The first column of this table estimates the integral obtained by the recursive trapezoid formula, with decreasing values of the step size. Explicitly, rn0 is the result of applying the trapezoid rule, this one here, with 2 to the n equal subintervals. Now, the first value uses just a single trapezoid, that is r00 uses the single trapezoid rule, and it's equal to 1/2 b minus a times the quantity f of a plus f of b. R10 is obtained with two trapezoids, and is given by the formula you see in the second bullet point. You can derive this using the composite trapezoid rule as they do on page 218. These formulas agree with those developed in the preceding section. And Rn0 can be obtained from Rn minus 1, 0, using the following formula. In general, we have Rnm is equal to Rn m minus 1 plus 1 over 4 to the m minus 1, Rn m minus 1 minus Rn minus 1 m minus 1. You may notice that this formula looks similar to the Richardson extrapolation theory from section 4.3, and we can actually derive it in a similar manner. Let's take a look at an example. So, if R42 is 8 and R32 is 1, what is R43? Well, basically we just use the equation from the previous slide for Rnm. And so R43 is equal to R42 plus 1 over 4 to the 3 minus 1 times R42 minus R32. That's 8 plus 1 over 63, 4 to the third is 64 minus 1, 63, times 8 minus 1, and doing a little bit of fraction work here, we get 72 over 9 plus 1 over 9, and that gives us a total of 73 over 9. Now, nice and easy, isn't it? Now, let's see how we can develop this into an algorithm. Basically, we're going to use the equation from before and replace n with I and m with j. So we get the following formulas for Rij and Ri0. Now, there are two ways to generate the array. One is to compute a reasonable number of terms for the first column and use extrapolation to construct the other columns. The other way is to compute the array row by row. For example, R11 can be computed by extrapolation as soon as R10 and R00 are available. The procedure Romberg that we're going to develop in this section goes row by row for the Romberg array for a function f in a specified interval ab. Let's take a look at the pseudocode for that. So here's the pseudocode for the Romberg algorithm. Now, this procedure is used with the main program and a function procedure for computing the values of the function f. In the main program, and perhaps in the preceding Romberg, some language-specific interface must be included to indicate that the first argument is an external function. Or you can simply call the function a function pointer, would work in that case as well. Remember that in the Romberg algorithm as described, the number of subintervals is 2 raised to the n. So what that means is we're going to need a modest value for n. Probably around n equals 5 is going to be sufficient. More sophisticated program would include automatic tests to terminate the calculation as soon as the error reaches a pre-assigned tolerance, like we did in the preceding lab. Let's look at how the authors use this program for calculation. So, as an example, one can approximate by using the Romberg procedure with n equals 5, the integral 0 to 1 of 4 over 1 plus x squared dx. And this is actually going to give us an approximation of pi, since you can see that it gives exactly 3 in the first iteration. It obviously degrades from there. Now you may recognize it as the 4 times the arctangent of 1.0, which we used previously as a formula for pi. Note that the columns in the last two rows are somewhat cut off, but you can see them in their full glory on page 219 of the textbook. Now let's look at how this relates to the Euler-Maclaurin formula and Richardson extrapolation. This section of the text explains the derivation of R and M using the formula for the Euler-Maclaurin formula. And the formula for that is the integral from a to b of f of x dx is r n minus 1, 0 plus a2 h2 plus a4 h4 plus etc. a6 h6 etc. etc. Now here h is b minus a divided by 2 to the n minus 1, and the coefficients a sub I depend on f, but not necessarily on h. So the error is O of h squared for the first column, O of h to the fourth for the second, and O of h to the sixth for the third column. Now, for the theory to work smoothly, it's assumed that f possesses derivatives of all orders on the interval ab. The basic assumption on which all the analysis depends is that the Euler-Maclaurin function is valid for the function f being integrated. Of course, in practice, we use a modest number of rows in the Romberg algorithm because of the 2 to the n constraint, and only this number of terms in the Euler-Maclaurin formula is needed. So there's the theorem that governs this situation, and that theorem is the Euler-Maclaurin Formula and error term theorem, and it says if the 2 to the m derivative of f exists and it's continuous on the interval ab, then the integral from a to b f of x dx is equal to the following, where h is b minus a over n, x sub I is a plus ih for I running between 0 and n, and the error term down here is really nasty for some xi in the interval ab. Hey, guess what you get to memorize for test 2? Anyway, observe that in the Euler-Maclaurin formula, the right-hand side contains the trapezoid rule and an error term. Furthermore, E can be expressed as the finite sum in the ascending powers of h squared. This theorem gives the formal justification and the details of the Euler-Maclaurin formula we saw in the previous slide. It also shows us how the columns converge as we previously described. So it's useful from a theoretical and practical standpoint, although we'll be skipping the proof. And in practice, we may not know whether the function f, whose integral we seek, satisfies the smoothness criterion on which the theory depends, that 2 to 2m derivative. What we can do is we can check the ratios to see whether the algorithm is working, and in particular this ratio Rnm minus Rn minus 1m divided by Rn plus 1m minus Rnm should be approximately 4 to the m plus 1. And we can check that to determine whether our algorithm is actually working out the way it should and whether that function is in general smooth. In closing, we return to the extrapolation process that's the heart of the Romberg algorithm. This process is Richardson extrapolation, which we saw in section 4.3. It's an example of a general dictum in numerical mathematics, that if we know anything about the errors in a process, then we can use that knowledge to exploit that knowledge to improve the process. The only type of extrapolation illustrated so far has been the so-called h-squared extrapolation. For general extrapolation, if the expression L is approximated by var phi of h, and if these entries are related by the error series, L is var phi of h plus a h to the alpha plus b h to the beta plus c h to the gamma, then an even more accurate approximation is L is approximately equal to var phi of h over 2 plus 1 divided by 2 to the alpha minus 1, var phi of h over 2 minus var phi of h. So, assume we're using var phi of h is equal to L plus a1 x to the minus 1 plus a2 x to the minus 2 plus a3 x to the minus 3. How can L be estimated using Richardson extrapolation? Well, part of the solution is to observe that the limit as x goes to infinity of var phi of h is going to be L, because again the x are raised to negative exponents. So L can be estimated using var phi of x for a succession of even larger values of x. And to use extrapolation, we have var phi of x. We do var phi of 2x and 2 var phi of 2x. And then we let psi of x be 2 var phi of 2x minus var phi of x, which is going to give a better approximation of L as x goes to infinity. This process can be, of course, repeated as in the Romberg algorithm. So here we want to estimate the limit as x goes to infinity of var phi of x from the following table. So we have this table of values. Here are the x's. Here is var phi of x, and we kind of want to know where it's going eventually. What happens as the limit goes to infinity? As we keep doubling x, where should we end up? What we can do is we can compute the values of psi of x. That's 2 var phi 2x minus var phi of x, and we get a new table of values. And here's the new table of values, and you can see that this winds up 12.3899, and so the limit as x goes to infinity of psi of x is, or var phi of x, is 12.3899. We can continue this extrapolation for another step as the book does, and we eventually get a value of 12.3900 with a round-off error. So this has been fairly short. Next time we're going to look at Simpson's rules and the Newton-Cotes rules. As a final thought, Bing suggests that I consider Rule 34 Simpsons when looking this up. Don't have a cow. It's going to be way lamer than the name would suggest, or anything that Bing comes up with.